Hello. 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 You're muted. Or people are muted. Yeah. Well, they don't necessarily want to be. I'm glad to see people coming in. Welcome to our meeting. I met with some of you this week again to talk about some things about different projects that you want to be involved with. I know Jesse's been talking about that as well, so with people individually. So I don't know if people want to go around. I think that would be a good idea to start. People could go around and give an update on things. If you have something that you've been working on, or conversely, if you have any problems or stumbling blocks that you want to address. Yeah, I can't hear you, Brian. Yeah. So I think that would be a good first step. Does someone want to go first? I know Brian's still trying to get set up here. There we go.
Great.
All right. Good. All right. So, does someone want to go first on what they did this week, or potential challenges, or if they just want to discuss something in more detail, any projects?
I'll go first, I guess.
Okay.
So this week I've just pretty much been doing a lot of reading. The papers that Jesse suggested that I should go through, and just other authors or researchers that I found that relate to this, and it's just been helping me pinpoint out what kind of questions I should be asking instead of a lot of the misunderstandings that we would have. One of my biggest highlights so far has been getting myself out of the mindset of, oh, can AI do this, or do we have technology that does this, and instead shift into how can we program this, or when we do, how would this work? Just because I feel sometimes I kind of before I even got into the reading, I was kind of asking myself the wrong questions of, oh well, how would this how does this work if we don't have the technology for it, when in reality we're the ones we're capable of making that. It's just a matter of when that's going to be happening and how that'll work. So being in that mindset now has really helped me just figure out the different parts of my research interests for this. So I was looking into papers that talk about empathy and emotion, and how that relates to the type of programming needed and how closely that relates to human emotion. How that could look in the future, what kind of technology is needed. Just in general, just looking through the broader aspects of empathy and emotion, and investigating how different types of learning machines work. So it's been a lot of exploring the past couple of days, but it has been helping me pinpoint out what kind of projects I want to be involved in, and how I'm gonna use the papers that I've read in the lab or in the work that I do. I want to contribute to the medium too, so I definitely will be writing something for that as well. And then next week I definitely want to talk about the childless hacker paper that Jesse suggested, because there are a lot of really good points that help me figure out what I should be looking at and how a lot of this work works.
Yeah, that would be that's a great update. Thank you, Sadhana. Yeah, I know we've talked about the childless hacker. We've talked about Josh Tenenbaum's work quite a bit in the lab, and that's a nice paper to keep going back to because there are a lot of interesting lessons there. And Yeah, so I think that's great. I think that's nice that you're kind of getting into the, you mentioned mindset and how you're moving from one mindset to another. I think that's uh, quite, good. That's exactly what we want to do. We want to change people's mindsets about things. Because oftentimes, before you start doing, even before you start doing research on something, if you know how to do research pretty well, but you don't know an area, oftentimes you will, have preconceived notions about what's going on. And then you go and you do the literature search and you find out about this area and you find that it's very different from what you expected. So this isn't just a challenge that you get when you're starting out or when you're learning, kind of how to do research. You're always doing this. This is always a thing. It's a challenge. So I'm glad you're making progress um, on multiple fronts. So next week, yeah, let's tentatively schedule, a little bit of. I mean, you don't have to prepare a really polished presentation on the childless hacker. We can, maybe have a couple slides where you bring in some key figures and, we can discuss it. So I think that's great.
Yeah, for sure. You're definitely right about that though too, because it was like before I came in, there were a lot of preconceived like notions about what I should expect or like what kind of things I would be looking at versus like now that I've kind of just like gotten myself into the reading aspect of it and just like understanding what we're doing and like helping myself like learn more about AI and like a lot of this, like a lot of the variables within the lab. It's definitely like a huge mindset change from like what I thought was happening versus what's actually happening. And I'm glad I'm there now because it's definitely the funnel like the funnel idea of like I started out so broad where it's like I don't even know where to go. And now it's just like more of like understanding where I am.
Yeah, very good. Thank you. Uh, so,
Yeah.
well, yeah, okay, Jesse.
Um, did I point? I don't know if I mentioned this to Brian, and I'll follow up on this later. But did I mention to you specifically, Sadna, the next there's a paper by Gary. I know I mentioned to you Josh Tenenbaum, who hit the childless hacker paper, and I'm really happy to go over that paper again because we mentioned that a long time ago and referenced it. So I'm really looking forward to that. But another paper that might help you frame things, especially someone new to AI, and I would kind of recommend this is kind of a cornerstone paper of like cognition future stuff in general. Um, is is one by Gary Marcus. That's not. It's not really. Honestly, it's not really even a paper. It's a preprint that's on the archive, and it's not published anywhere. So you can make things that are important and go on preprint in the archive and never get published, but still matter. Which is that's a whole. If you don't know anything about what I said and that all those terms mean nothing to you, that's fine. But we will eventually get into what all that stuff means because what I just said is like almost radical compared to the publisher perish narrative. But anyway, just very brief context of Gary Marcus is a very major critic of hype about where AI is right now. Gary Marcus is a cognitive scientist. He's on a particular side of the AI debate about what it takes to make AI more robust. And there's a paper there's a preprint, as Mecca should call it, that he put on the archive a while ago that isn't really, it's more of a thought piece than a paper. It's not like a prescriptive thing. It's just his ideas, and it's called The Next Decade in AI: 4 Steps Towards Robust Artificial Intelligence. And yeah.
Yeah.
Yeah, I was gonna do that. So yeah, and I think I mentioned that to Brian, or Brian already knew about that. But for people coming into the AI debate and don't have any context of what AI really is or does, not like when you hear about AI in like common parlance or terms of speaking, everybody says it does all sorts of different things, and it does amazing things. But it's important to understand what can be done now versus what can be done later. And the paper that the Gary Marcus paper about the next decade in AI is kind of like looking at specific areas that it's currently limited. So we'll talk more about that paper in general, but I don't know if I sent it to Sudden or not before. I don't think I did. But I mentioned it just broadly right now for anybody who kind of wants to get like the maybe somewhat critical or like what is AI lacking right now that maybe could change in the future, from someone who's on the cognitive science, cognitive structures. There's more going on than just deep learning perspective, and it's kind of a hype checker of sorts. Or at least what Gary Marcus tries to do in some ways. So that's all I'll say about this. There's more to say about it later. But great update, and if anybody else would like to talk, you're welcome to do so. So thank you. I can't.
About Shima.
There we go. Okay.
Yeah.
Nice.
Did you have another?
Shima or Sam? Or would you like to?
Or Sam?
I know I had a meeting with Shima this week, so.
Okay. Yeah.
But...
Oh, sorry, I was cutting in and out. Were you saying my name?
Okay.
Oh, okay.
I can hear you. Yeah.
Okay. Yeah. So this week I joined the Critical Periods in Development Discord, and I've been doing a lot of reading about that. So I met with Jesse, and he suggested that I sort of read the articles and try to like categorize them into subtopics, because I feel like there's a lot of just general information on critical periods, from things like sensory development to like learning language, and things on like continual learning as well. I've been reading about critical periods and language in particular, like how long the critical period is for learning language, and what happens if you miss this critical period, and is it possible to learn language after that? And then I also started reading things about continual learning in reinforcement environments, and how AI can be developed to mirror child development, and sort of like using it as a tool to like basically teach AI how to do like to learn like open-ended skills. So yeah, basically just a lot of reading and like trying to categorize it, and trying to focus on like a specific topic that I can eventually do a paper on or something. But yeah.
Yeah, thank you, Shima. That was very good. Yeah, so I know Jesse met with you. Maybe Jesse wants to talk a little bit about that as well.
Sure. I'm actually looking up. You don't have to read this paper, but there's actually a lot of overlap between. Well, there's a decent amount of overlap between what you said about critical periods and child development and the paper we actually just mentioned that Sudden looked at about child as hacker, Josh Tenenbaum paper. Josh Tenenbaum is a cognitive scientist himself, and he's really interested in these sort of, not actually critical periods, but these like big broad stages in human development, from like early stages in fetus development, like child, and then infant and child and teenager and adult, and like how there's different the cognitive capacity of humans is not really a constant thing, and there's a whole, this leads into a lot of discussion about a lot of early work on intelligence and cognition or whatever was originally done in the sense of a very limited sense of an adult male in like the prime of their intellect or whatever. Maybe like there's a very specific segment that people interpreted intellect being at one point, and there wasn't always a focus on development necessarily. So being more modern and more developmental, and there's great people like Piaget and many people who have been interested in development as part of it. But Josh is really interested in sort of these different stages of how a human being has different capacities over time and what affects that and how to grow them out. And that's not necessarily entirely what Childless Hacker is about, all of it, but I think it'll be interesting to hear you and Sadhna talk about that next week. And you can look at the paper now if you want to. I'm going to put that in there too. I just pulled it up. I don't. This is. I'm trying to find a link that I actually like for it, but this is okay. But yeah, that outside of that, outside of what Simon just said, it kind of led to, you can see in the background, I've done a few different versions of this, of like a really interesting discussion, and with it, all of the interns really, you know, there's that really cliche phrase of how, oh, when you teach new people, if you want to learn, teach, or like when you teach people new things, you learn them yourself even more, kind of a thing. And I think one thing that's coming through, and something that also just new for us in the lab a little bit, is talking about the different types of things we're doing in the lab, as opposed like, and through talking to Shaima and talking to Bradley after that. I met with Bradley this week also. We also went for like switching paper, some other stuff. But one thing that kind of came out of the discussion was, you know, what are some different things in the lab in terms of like a research group or an interest or a group of interest and some external collaborators, what's a very specific implementation we've done, and kind of giving some differentiation between what those things are in a little more clear sense. So I'll say more about that later, but that was a really interesting thing that came out of trying to explain the context of the lab and what's going on. Also, a little bit of a shout out to Levy flights or Levy walks, which are a really interesting thing we might talk about later too, which is like a very early explore, exploit, a very fundamental to biological life explore, exploit process of doing reading a bunch of papers in this area and then maybe jumping to a very different area because you're kind of exploited this resource, this potential area. Now you're taking a big jump over here, look around a little more, and maybe jump over here. So more about that later too. A lot of interesting, it was a good meeting, and I learned a lot from it because I rambled a lot, but Shaima had a lot of good questions, and it was a nice meeting. And anytime people want to meet, plug for, just say, hey, Jesse or Bradley or both of us, and even other people in the lab, you can meet whoever you want to, and it can be a very nice thing to do, especially if you want some context or whatever. So yeah, that was great. So yeah, some things, every time these updates come up, there's a whole bunch of other things that could be said about them, and maybe we'll come to them later in the meeting or next week or something. So yeah. Okay. Sam, did you want to say anything?
Sure. So this week, I was kind of like everybody else. I was trying to focus on reading and gathering sources for my topic that I was planning on researching. And through like researching, I found out more about the four main types of intelligence that are incorporated into artificial intelligence. And one of them did happen to be like a whole section about empathetic side of artificial intelligence. And then going further into that, I was starting to realize like how artificial intelligence actually identifies like empathy or looking at human emotions, which is, I kind of like just trying to figure out what type of, I guess, like technology, because I know it's not like a neural network, where it's kind of like a neural network, but I didn't know if there was something else I could compare it to see if there's like a different type that does it better. So that's kind of where I got stuck looking at, see if maybe there's something that's a little more efficient than a neural network that can identify human emotion a little bit better. So I was kind of, that's where I kind of got stuck this week. And then I was trying to focus a little more on, I guess, defining like the different types, like the different ways AI can sense emotion. So through like text, audio, and video. I found a little bit of information about that this week too. And I guess like my next steps would probably be, I do want to schedule a meeting with one of you or both this week. So, and that would just probably be where I'm at.
Great. That's very, very good things to come across, very good questions to have, especially for people who aren't familiar with AI that much. It's so, I don't even know how to really begin. Like there's sort of so much of when people talk about AI, it means all these different things, and then part of like, there's like a bit of cold water or like deflation, but also excitement to realize where things are happening right now and where is the limitations coming from in methodology, in what AIs can understand, and also like, as you're kind of getting at, in techniques. Like a big thing when I presented my paper, Ineffective Computing, which is kind of affect, is an AFFECT. I was at AIII Symposium, which is a very like it was like their symposiums are very like people beginning out or like new ideas. So it wasn't like the biggest conference in the world, but it was a really cool thing to go to. And that was like 2017, and at that time, deep learning was still like kind of seen, even mockingly, as a bit of a savior. And there's maybe some turning away from maybe deep learning in and of itself, and just more and more and more and more and more neural networks maybe aren't the solution. And there's a whole kind of AI winters and like the ebb and flow of hype about AI and what AI can do, and like, okay, when people really figured out deep learning and the computational behind it in 2012, 2012 was a big kind of, the 2010s, and this last decade or so has been like the deep learning era. And now maybe we're hitting a crest in how amazing that is. We don't really know yet, but these are great questions to have, and nothing we can really answer. There's no definitive thing about it, but one thing that it's great to have discussion about and bring up in the lab, and everybody's mentioned so far, is, you know, what are the limits? What basically is the state of the art right now? What has been done in the past, and where are, like, in terms of empathy, in terms of critical periods, in terms of interpreting emotion, in terms of understanding stages in development in a human being or in a natural system versus a mechanical system or an AI. These are all really great. These are super good questions to be asking, because you're starting to get the context and understanding, especially if you're very, you hear all these crazy things about AI sometimes, and it's like, well, AI is really great at this stuff right now, and maybe has limitations in this area, and how people are trying to push those limitations forward, like that's really what the cutting edge is, and there's a lot to say about that. So that's a very legitimate update. You want to say, Bradley? I kind of model. You had some like thumbs up and other things. So
yeah, so I think this is great. And I encourage people to, you know, just spend like your week reading. I think that's a very good way to sort of get immersed into the area, and you know, sort of, you know, maybe pose and repose the questions that you're thinking about. So, you know, if you have a different question than what you started out with, that's actually a pretty good thing, because it means you've engaged the literature and you're understanding what's going on. And is in terms of like, you know, we think about neural networks as sort of being the be-all end-all sometimes of artificial intelligence. I mean, that's the shorthand almost. But that's actually not true. There are a lot of other models that people use, such as finite state machines or Markov models that can be used, that model essentially states. So if you think about like what a neural network is, it's a network, it's sort of what you might call a connectionist network, which is you have these nodes that might represent simple things. It might represent, you know, neurons or some information that's being collected somewhere. And then it's exchanging information with other nodes, and this does this in a way that's sort of all-to-all. So there are all these connections. And then the algorithm basically associates things in a certain pathway. There are weights to these connections, and things get pruned down, and this is how you get a network that gives you an intelligent output, or at least, you know, it does something that looks intelligent, like classifies a bunch of things into categories or recognizes patterns. It goes from the top to the bottom, and so it's a directional network, and then it just processes information through there. I mean, that's usually what we think of, very classical AI. Deep learning even works sort of on that principle, although it's much more complicated. But you also have models where you can go back to the brain and go back to the behavior and say, you know, there are these states that we recognize, and especially with like in affect, you have affective states. And those states can be modeled, you know, with like, you know, we call it a finite state machine, where you have different states that are little circles, and then there are transitions from one state to another. And that transition is expected to happen sort of at random, but you end up, if you have a model that gets trained and that exhibits these sort of affective states, they have a probability to them. And that's what we call finite state machine. So I'll talk about that later. Maybe I'll do a sort of an impromptu chalk talk about that. I'll draw it out. You know, there are other models other than your neural networks, and they're actually quite good, especially if you have data underlying it, especially for like human-computer interaction, or like human-computer interfaces or brain-computer interfaces, where you have some signal from the user. Could be like behaviors, it could be like brainwaves. They go into this classifier. The classifier figures out what the state is of the user, and then it gives an output. And then it looks at like how those states change over time. So that's when you get those transitions between states. And so there are a lot of ways that you can do that using a very simple model called Markov models. There are other tools as well that people use that aren't neural networks. We do things with agent-based models in the group a lot. We haven't mentioned that too much, but I think that's something we can work on in terms of methods and techniques. We have a lot of, you know, you can get really proliferative. You can have like a technique or tool zoo where you just like, you know, especially like in something like genomics is a good example of this, where you have like 50 different tools. They all do slightly different things, and then people get hung up on those distinctions, and like you're not answering your scientific problem or question. You're just like you're reciting the tools, and which is, you know, understanding the tools is good, but it's like we want to sort of understand them in the context of the problem. You know, what given a problem, what techniques do we want to use to solve that problem or to get some insight? And sometimes, you know, it's an obvious answer. Sometimes there's, you know, maybe there's no tool for the question you want. Maybe there's no good way to model, say, for example, the behavior that you want to model. So that's a possibility. But in most cases, we can find this in the literature. And it isn't just, say, throw a neural net at it. It's, you know, we'll find a model that has, you know, every statistical model, every computational model with certain assumptions. You know, what do my maybe input data look like? What does the phenomena I'm interested in look like? And then so we can go from there and then apply the correct method. So I'm glad people are thinking in terms of methods, in terms of problems, and we'll build from like our problems. I think in the next few weeks we'll start getting more into methods of how to deal with some of these issues. So very good progress. Thank you, Sam. Jesse.
Can I say? Oh, what were we gonna say?
Well, I was going to go to
have
Brian,
a
but
point I
yeah.
Oh, I know Brian will get this, so I
Okay.
kind of want to make this segue. One thing to think about in terms of AI, especially for people that are newer to it, we talk about deep learning as a method right now or a technique, but the flip side of deep learning is basically big data. If you don't really know what big data is, it just means like having a whole lot of data, like lots and lots and lots and lots of data. Because deep learning only really typically does well if you have a lot of data to train it, particularly in really applied models that, like an example, in a place that I'm working, I'm going to be very vague for a variety of reasons, but we're trying for months to get access to certain data sets so we can train these models that we want to use in the product we're developing. And it's so hard to find a robust enough data set that's specific to the needs that we want to find. There's a lot of similar data sets that have similar things, but we're basically doing something with computer vision. And it's hard to convey how I wish someone explained to me a little bit more of this earlier in my career too. Like data is basically what a deep learning neural network feeds upon to grow strong and do things. And it's tough because many deep learning situations are still in the context of narrow AI, and they're really good at a very specific, a very exact process of doing things. And if you change them a little bit, they tend to break or not be very, they can be very brittle. They're not very, if you train a neural network or a set of networks to do one very specific thing, be really, really good at it. AI currently tends to not be the most robust or strong AI. Like strong AI versus narrow AI is kind of a debate, and those aren't really exact terms, but part of why, like in a very real world, not theory, not hokey pokey, like right now, people wanting to make money right now, I am in a situation where literally for 3 months we have been trying very, very hard to get access to certain data sets that have been accumulated with a very specific purpose, and it's hard to do to make a proprietary product and get access to them and go, like, some things are have very strong license for this can only be for certain research or for academic purpose or this or that, and getting the right data is a huge thing right now. That's partly why Facebook and Meta, which we'll talk about later, is such a powerful entity as it is right now, because they have access to so much data. And that's also why deep learning has a lot of inertia behind it, because deep learning is intrinsically tied to big data. And if you're someone who has big data and you want to sell that data so people can train their models, that's a big, like, social, technical, political, economic reality that's affecting all kinds of research and all kinds of developments and things. So this is a very, I'm totally giving you a super, super broad brushstroke. Also with a very real, like what I said is totally true. I'm not exaggerating at all what I said about how hard it is to find a specific data set when you're trying to, in this specific case, like having the right data set and needing to have a lot of it. You can have a very nice model, but if you don't have a proper data set that's robust enough to train your stuff, or the means by which to acquire a data set, which is a different thing. So I'll say that, and then very quickly, kind of going back to when we mentioned that first paper, and Brian just posted a link about, like, towards socially aware AI and effective computing. One of the big things that come with that, in a scientific sense, in terms of like maybe thinking about empathy or periods of development, whatever. When I went, even when I having flashback, all these flashbacks from the conference, one of the things that my PI at the time, Dr. Kim, was like talking to people on the side about, was like, yeah, how do we get to a ground truth? How do we get to something that's more than just sort of a conjecture? Because emotion isn't really, you can't really just hook up something to your brain that says, oh, you're feeling exactly this emotion in exactly this degree. Emotion, or the way things are constructed in what we call emotions, aren't necessarily clear-cut things. So how do we get to a ground truth about emotional states? Does it even exist? How can that be measured? Those are like really hard questions, and those are really deep scientific questions, and kind of get to the limitations of what, you know, some questions don't have very clear answers either in methodology or even in science. And there's been a huge amount of effort trying to categorize emotions and social context and valence and Ekman's emotional categories and all these different like ways of triangulating what emotion or cognition or whatever means. And it's like, you know, there's kind of there's a lot of competing notions about how to best go about that. So I say all this as again, context to flesh out later, but if any of those questions come up later, or like I'm saying things, or Bradley says things that you kind of want to hear more about, or as you do your research, you're like, oh, I'm starting to see this thing that we mentioned maybe today, just feel free to mention it and go from there. So these are very incomplete, broad brushstrokes of, oh yeah, here's some very general context, and if you maybe it lends you somewhere that you find and follow up on later. But thank you for the digression and interlude, and Brian, you can give your update if you'd like.
Sure, thanks, Jesse. It's always a pleasure to hear all these kind of tangential but very applicable situations or concepts surrounding the things that we're discussing. So I really appreciate it. And you mentioned earlier about Gary Marcus. I actually had not known of Gary Marcus until you guys, Bradley and Jesse, mentioned it to me. So I've been diving deep. Actually, that paper that Jesse was talking about is now also a book called Rebooting AI that just came out, I think last year, and it's really good. I can't recommend it enough for thinking about the limits of neural networks and how to build stable AI that we can trust is kind of the subtitle. But I digress. So let me stop digressing. I'm working on two main things right now for the lab. One is hopefully we'll be able to get it finished this weekend, an extended abstract on switching theory. And that's with Ankit, Daniela, Amanda, Bradley, and Jesse. We're all kind of contributing, and we had a meeting this week to kind of narrow down our thinking. And we've got a shared Google Doc where we're just kind of working out the details of that. So there's a lot to unpack there. Yeah.
Could someone post that link in the chat just so people can see it? Like it's if any people want to join in that, you're welcome to do it. Yeah. But you don't no pressure to do it either. But just I don't think I've seen it since like yesterday or something. But
yeah, it's been a link that lurks around in the switching theory channel. So yeah, I'm happy to there it is.
If Bradley, you were going to talk more about that later.
Well, yeah, I'll talk more about that later. I want to go over it. I think Daniela wants to see. Yeah.
Absolutely. Okay, I won't go further into it then, but that's just something we're working on, and the deadline for that's coming right up, so it's very present. The other thing I'm working on is making a presentation for NYCWC, New York City Women in Computing, about the interpretability issue and techniques of employing ethics in AI. So trying to keep AI in a way empathetic without referencing effective computing explicitly. But I really like that mode of thinking, Sam. It's really exciting to hear that other people are kind of thinking in this direction. But basically right now I'm putting together a presentation that focuses on interpretability, how to how to basically pragmatically interpret a black box neural net, or how to figure out what like how to interpret what these more complicated mathematical models are saying in kind of human readable language. And then also looking at techniques of embodied or enacted AI systems, which is something I kind of heard mentioned in a meeting and kind of on the Slack channel about these related to this book called, oh man, I'm reading it right now, but I can't remember what it's called. The Embodied, sorry,
Embodied mind.
The embodied mind. Exactly, the embodied mind. So I'm deep into the embodied mind. I'm deep in Gary Marcus and Lou Lam and Ron Sun. And I'm also reading a book called Data Feminism by Catherine D'Ignazio and Lauren F. Klein, which is excellent, and looking at the work of Timnit Gebru, and just kind of trying to put together a presentation of what, like where ethics, the issue of holding AI accountable is right now, and what the techniques are that we have, and also maybe presenting my own research, which is this idea of once we get a model for interpretability of a neural net model, like once the model's already been made, so after the training on the data set and everything, is there a way to kind of take that interpretability and basically stick a terminal on there, or stick a, like, I'm thinking of using a programming language called Datalog, and if we can interpret the content of a neural network model as a logical structure in Datalog, then it might be possible to use Datalog as like a backend to kind of rearrange the model and to investigate the model and change it pragmatically. So that's kind of where my thinking's at right now, and these are the things that I'm working on.
Good. Yeah, so that's great. You have a kind of you're spread out across a couple of areas, and that's good. And then you have I think you have a good handle on the reading. Have you encountered any sort of shifts in your thinking as you've been doing this reading? I'm just curious.
Oh yeah. Yes, constantly.
Okay.
Especially with regard to the switching theory, the AI ethics I've been thinking about for years. So it's been shifting, but not as radically as it is in switching, where I'm not as familiar with a lot of the examples. So it's really exciting to be in there.
Yeah, that's great. Thanks for the update.
For people who don't really know, this is just a general comment about like AI ethics stuff, and you hear about like black box models and how difficult it is to interpret what some AI models are doing. Like even at Brian mentioned like, oh, could I go into the MIT AI ethics rating group? I can send you the notes that they're doing, because I didn't even get to go this week, honestly. I had a very busy Thursday, but I can send you some, like here's I'll put this just in the chat. Oh, that's the wrong one actually. Where did it go? Well, I don't know. I'll put the resources in later. But my point was going to be, AI ethics. There's a lot of different approaches in terms of like sorting out ethical issues in data before it's put into like the machines or like the models, and then there's a lot of things being done about how to sort of tag things going through the model, and that's a very difficult thing to do, like interpretability or explainability, like what the AI being able to explain what and doing how it's making it, and that's kind of like a major battlefield. And it's sort of like this is, in a very high level view, this is really challenging and a major, why is it such a big deal is because when people are trying to regulate at a legal level or like a procedural level, what to do, it makes it really hard what to do when you can't measure very well what's happening. So when we hear about interpretability or explainability in the context of AI ethics, the big question is, how do we measure what's going on in some of these big machine learning models? Because we don't really know. And it's great. It's almost humbling because I met like MIT. Like, oh, it's a really cool place with really technical people, and a lot of this stuff it's just people like, here's our best effort for what we currently can do with the technology, and it's actually quite humbling to realize that, well, we can really look at some of our causal mechanisms and our causal models, and we can apply these things to try to sort out the data. But we have major limitations in explainability, interpretability, and until we have a technical breakthrough on that end, or we design our neural networks differently, we're kind of like caught between a rock and a hard place is a phrase that doesn't really work, but it's sort of like, it's like you're kind of trying to herd cats very weirdly, and I know that's the awkwardness of me trying to explain this kind of mirrors the awkwardness of the situation, because there's just not a lot, there's not really a lot that can be done, and there's a lot of good effort, a lot of brilliant people trying very hard to care about this topic, but it's sort of like hearing like some really brilliant people care about it the way that they do, and what we can do right now is just like, well, here's our best effort, and we're going to try to create best practices and regulation that is like, the ability to regulate and enforce it even is a whole other political issue, that who's going to regulate whatever a Facebook or Meta actually creates? Who's going to know how to do that? That's a whole other issue. So for those who have no context about AI ethics, that's a 2-minute preview of what the hell is happening or not happening in that area. Bit Wild West. But also a slight preview of things that we might try to talk about at NYCWIC, or New York Celebration of Women in Computing, which is not an ethics conference, but we have like a few years of going there and presenting about ethics, which is really cool. So yeah, that will segue into my talk about that whole. I'm going to talk a little about that later too, just to give an update where we are with that. So that's a little bit of a preview for that too. So okay, Bradley, I think that's our updates for. Do you have any updates for this week, Bradley? I guess I have two.
Well, I have a couple. Well, I can talk about a couple things later. I wanted to get to. Actually, I wanted to offer Christian an opportunity to. And I guess.
Oh yeah, Christian.
Yeah, he hasn't been here in a couple weeks, but if he has anything he'd like to talk about or update, and then we can move to Jesse, and then I can move to my updates.
Hi everyone.
Hi.
Hey Christian.
Hi. So yeah, it's nice seeing you. Jesse,
Yeah,
is this
yeah.
Boston University hat? The cap you're wearing, is it Boston University?
No, this is actually I am a poser. I have no right to wear this hat. It's actually an Oxford hat, but I got it when I went to Oxford in person, and I went there for a business trip, and I was really proud of it, and I don't care, and it looks good on me, so I wear it when I can, and when I don't want to show my messy hair, like today. But it's from Oxford. It looks cool. So
Cool. It's really good.
I always feel like the slightest bit of a poser, but like I have a great story that I won't get into about why I was there and what happened and how I came across the hat. And this hat has been through so much, like there's just so many stories associated with this hat. So it's like it's a cool university, and I'm an academic nerd, scholar, poser thing, great. But so no, it is Oxford, but stories some other time. If this was like let's go out to the, I'm not really a big let's go to the bar and talk person, but like in that comment of I would have an after party and talk about all the stories associated with this hat. But yes, but thank you for asking about it. How are you? What's new with you?
Okay, so for you can say past couple of weeks, last 2 months, I have been working with an open source company. So they are the first to make vectorized database for AI applications. And currently I'm working on an open source project called Tohi. I sent you the...
Oh, that's what you sent me. Yeah.
Yeah.
Cool.
So, okay, so on that, we also got accepted under Python Software Foundation also. And I wanted to, collaborate with Orel or Divomum also, to get some very broad journals, broad usage pipelines. So, okay, so this open source project is used to create pipelines, machine learning pipelines, which are very easy to use. You can do a lot of work with just 5 to 6 lines of code, and they're very production friendly. if you want to do the DevOps and that stuff, if you want to scale the application, it's like super friendly. So yeah, I've been working on that a lot. I didn't get a lot of time to do stuff with Orel nowadays because I have this full-time job and I have my master's degrees as well. So apologies, I'm not contributing the way I should be doing it. But yeah, in the coming weeks, I'll try to do my best to contribute more.
Yeah, no problem. That's great. I'm glad that you're finding success. I was looking over the Tohi materials. It looks very impressive in terms of like what's there. And so I know you're applying to Google Summer of Code through, if our organization is accepted, and we're still waiting to hear back about that. We'll have maybe a spot for someone to work on these pipelines, but even if we don't do that, or someone doesn't get accepted by Google Summer of Code, we can still work maybe a longer term on some of these pipelines, because I think it's nice to have something that's automated for people to jump right in. And so yeah, our DevaWorm group actually has been doing a lot of work with like deep learning and pre-trained models and things, and we're kind of moving into graph embeddings. And it's kind of hard to we could build the software, but we can also build a pipeline or have some way to manage some of these projects, especially as we have multiple projects or multiple sort of components. So yeah, I think that's great. And of course, in the lab here, in this set of groups, we have we want to find methods for implementing some of these topics that we're talking about. And, having pipelines would be great, because it would be easy to sort of have something that's replicable, and, we can do things. We don't have to worry too much about fiddling with the models, and that eats time, and we want to actually just use them in some cases. So.
Yeah, that's what my plan was to, work on some biology related pipelines with DevaWorm. And because a biologist, he or she doesn't need to spend too much of time on working on the code. So that's why if we are able to automate that kind of stuff, that would be awesome. So yeah, in coming time I'll be consider a lot. Maybe we'll wrap around Riverrun and automate some of the processes into Tohi pipeline. And since these are saved in the Tohi hub, you don't some of the dependencies issues are solved itself. So all you have to do is call the pipeline. No need to the dependency has you don't need to go through that. So yeah, maybe in coming time, I'm not sure 100% sure about. Then coming maybe we can do something like work on AI ethics, make some pipeline that maybe detects racism, detects sexist comments, maybe work on something that on that. That's just something idea in back of my head. So maybe in coming time, if everything goes well, maybe we can make something like that also. A ready to use thing where you just put your text and get that whether it is sexist, racist, or something like that.
Yeah, it would be great. Yeah, we'll talk more. Yeah, we'll talk more about that in coming weeks. I know we have the Google Summer of Code project on AI ethics, actually, that is we have the two parts. We have the one part where you would develop a model for sort of, it's an open source sustainability project. So it's a little bit different than the typical AI ethics topics, but it's the idea of, creating a sustainable open source community that, is free of a lot of the problems that plague certain open source communities with, aberrant behavior and people just kind of free riding on it and things like that. So, building a model that sort of, allows us to sort of avoid a lot of those pitfalls, or design it in a way that, facilitates interactions, smooth interactions. And then there's a second part where there's it's an agent-based model approach where you would simulate some of these communities, and it would generate some rudimentary data that you could then use to validate your model. So that, that's something that I've been talking with some people in the Slack about this week, and I haven't been able to. I mean, you know, it's like with the Google Summer of Code projects, I want people to kind of think about it and come up with their own solution. I give them some guidelines, and then they have to come up with their own solution. But, you know, having tools like that, I think would help people sort of get to the solution instead of like thinking, well, what technology do I use? How do I implement this exactly? So, I mean, you know, this will be useful, I think, for some of these other projects where we want to do things that are pretty advanced, but you don't want people to spend like 2 years figuring out kind of what tool chain to use. Yeah. So thank you, Krishna, for the update.
One more thing, like still Orel is, you know, participating for the first time in GSOC. So if you want me to write some onboarding documents like I did for DevoWorm in the previous year, so I'm down to that. I'll be doing them. And if you want any, you know, some kind of poster or something to be, you know, sharing, I can do that also, you know, if you want me to do that.
Yeah, that'll be coming up. I know we were talking about like onboarding materials for the lab, and we have some for DevoWorm just for GSOC. So we might actually use some of those over, but we want to update them. And yeah, so and probably improve them as well. So yeah, let's talk about that later or coming in next coming weeks, because I guess we'd have to wait officially until we're accepted, but even so, if we have these projects going, we want to have a entry point.
Great update. Great to hear from you, Krishna. For those who don't know Krishna, I haven't met Krishna before. Krishna was very active last year and in the past, and worked with us on some things for a whole lot of things in a lot of ideas from like some things in machine learning and some of it applying to AI ethics and some other topics. So a great resource to have. And another plug, like if there's somebody who says something in the Slack or you see an older comment, feel free to, you can direct message them in Slack and they might respond. Like I hear things from Rashad and Krishna, and Ankit's, you know, more around too. But a lot of, you know, or like people maybe don't even know who Daniela is, but you'll see her active in the Slack. Daniela, I don't think ever has come to a Saturday morning meeting like this, or Saturday in Eurocen morning in the East Coast. Well, you know, like, you know, people are in India or other parts of the world, or in Europe for Daniela, and she's in Italy. And there are a lot of people in the Slack who are in the lab. Not everybody who's in this meeting is here. And just so you know, Krishna, like most of the people that spoke earlier today are newer interns. So if you haven't met them, they're good. We finally set up an intern program to my old university, University of Albany, and a lot of these folks are from that, or like undergrads in that, kind of like joining through the university to find us here for like an internship or yeah. So that's kind of, you know, that's a little bit of context for everybody too. But yeah, for the newer folks, feel free to reach out. And for Krishna, again, great to see you. What did you want to talk about next, Bradley?
Well, why don't I get into, I wanted to give a short, I was talking about earlier about the different models that differ from neural networks. So I might give a short little chalk talk about that. And then we'll go to Jesse's updates. I know he has a number of updates. So I'm going to share my screen here, and I'll get to the comments in the chat after this, but I want to, so I'm going to use my board here. And so we talked about like neural nets, and everyone's familiar with sort of the connectionist model where you have these nodes arrayed in layers. So these are nodes. These nodes resemble neurons. They don't really have all the features of a neuron, but they have two features. They have they have sort of these connections that are that mimic synapses because they interface at the edge of the cell, and you have these two different connections between these two different cell types. And of course you have the cell body, which isn't modeled as a cell body, it's modeled as a unit that has a state. So like these edges here of this network have different probabilities of being activated. These cells are being activated through them, so the higher the probability of this connection being activated, the higher the probability that these cells are activated. And what you do is you put information into the top. I mean, this is a very broad overview of this, so this is very simplified. You put information into the top layer, it gets processed through these different layers. These connections between the cells have a certain weight, so you end up with something called a weight matrix, which is usually denoted as W sub ij, and that's a matrix that just measures like every cell versus every other cell. So you end up with, you know, it's not a sparse matrix, but it has like, you know, if you want to look up a weight of a connection, it's this cell versus this cell. You find it in there, and then that's your weight.
Can Bradley's screen?
Okay, I just sent the chat into. It's currently black for me.
Okay, let me reshare my screen.
Yeah, I was. It. Yeah, I don't know if it was like.
Yeah, I don't know why it's okay. Can you see my screen now?
You're frozen currently for me.
Oh, well, maybe it is frozen. I don't know why. You can see my face, or you can see my screen. I don't know.
You saw your face, and now it froze, and now I see your face again.
Okay, let me do this again. Can you see my screen now?
It went to when you're sharing your screen and it's showing the expanded view, but it still shows your face, and now it shows a black background.
Let me try this.
Your BA.
So there's a.
I had some issues with sharing last week too.
Yeah, this I might try to.
You're trying to share like your mirror board here. Oh, I just saw it.
Okay,
really
here it is. This is it. Now, can you see something? It says I'm sharing the tab.
I saw it. Then it went away. I'm still seeing nothing.
Oh.
Again.
Well, I can do this, and then you can watch the recording of it. So, you know.
I don't think it's being recorded though.
It is. It's fine.
It's not appearing on.
Oh, it'll happen. It'll be fine. So why don't I go through this, and then you can see it later. I know this is kind of difficult, but I can also share the images in the channel so people can see. So anyways, you have this network, and you put information in the top, and you go through and you have this weight matrix, W sub ij, and you can look it up, the intersection of these two cells, this weight. And the idea is over time these weights change based on the data that's coming in. And then, you know, you can put a threshold on these weights, on this weight matrix, and see everything with a low association gets removed. So if you remove those, then you end up with a weight matrix that has edges that are the most commonly activated, and that's your pattern of activation. And then that gives you an output out of the bottom of the network, which is like maybe some set of classifications or identifying a pattern. There are ways you can set up the problem so that you can set up your network to have, you know, this weight matrix. You can play around with it in different ways, but basically that's the idea. You have this weight matrix. It gets pruned or thresholded so that you only have the strongest connections, and that's your pattern of activation in that network. In typical neural networks, you have like 3 layers of cells. In deep learning networks, you have like 20 layers of cells. And when you have 20 layers of cells, there's a little bit of difference in the different layers. In the top layers, there's a certain type of processing that goes on. then the next layers down, you have other types of processing that go on and so forth. So it becomes a little bit, computationally it becomes a little bit specialized, but it's the same principle. You end up with this set of weights that represent this pattern of activation that represents some answer. It could be a classification problem where you have different classes of things. It could be like some other thing where you're recognizing patterns, where the pattern is one way or another. So that's basically what you're answering with a neural net. Now, if you go to this other types of models, and especially in like affective computing, or in human or in brain-machine interfaces or brain-computer interfaces, you have a different type of model people use, and these are what they call Markov models, or finite state machines. And it's basically the same idea. The idea is that these are all the same idea. They're different from neural networks. So what you'll have in a Markov model is you'll have different states defined. So you'll have a problem, and think about this in terms of breaking a problem down into different discrete states. So, if I think of emotions, I think, there are a certain number of emotions that you can observe in humans. There's like anger and love, and, but you know what those are. They have finite limits. They're boundaries in edge cases. We don't care about that right now. What you'll have in Markov models is you'll have, let's take two states, like A and B. And I'm drawing like two circles labeled A and B. So this is like a way to sort of characterize this. So let me get this back. Okay, I want to redraw my B because I kind of made a mess of it. And so these two states are separate things. And we want to ask the question over time. So we have a time series here that we're observing. What's the probability that our system will transition from A to B or from B to A? And then there's a further probability that things will stay the same. So we have these like self-transitions. So the question is that we have the system that's currently in state A. And we want to ask for every observation in time, what's the probability that you'll go from A to B? What's the probability that the system will stay in A? So for that system, you'll have like a probability, let's say it's 0.5 that it'll transition and 0.5 that it'll stay in place. That's kind of a random probability that things will either change or stay the same. So let's say that it stays the same for a couple of time observations. So we can actually build a table that says time, state, we get TNS. We have a table, we have 1 through like 10, and it always stays in the same state, A through A. Okay. Now, let's say on the 11th observation, it changes to B. So now we know that it changes to B, and we also know these probabilities 0.5 and 0.5 are wrong. So now we have to update these probabilities, and this is something that you see in a neural network where the weights update. So you have a weight matrix that gets updated. In the Markov model, these probabilities get updated. Okay, so these probabilities get updated. So now your probability is something like 0.09 for going from A to B, and 0.91 going or staying in A. So it's a different, now you're updating your probabilities here. So now, you're in B, and 11 is B, and 12, you might stay in B, and then now your state transitions from B back to A. And so now you can say that these probabilities are staying in B is 0.5, and going from B to A is 0.5. So now you have these transitions. Now, why is this important for emotion? Well, it's because if you're measuring emotions as discrete states, you transition to different states of emotion. You define those states a priori, which means ahead of time. You can then model them as these discrete states, and you have transitions between them. And what you want to do is you want to get your data and observe it and say, what are the probabilities of these transitions over time? And so if I say I'm happy and I'm looking at someone who's happy versus someone who's sad. I want to go from being happy to being sad. I want to see what the probability of that is, or I want to see what the probability of going from being sad to being happy is, or what's the probability of me staying sad or staying happy. And so we can answer all these questions with this simple Markov model. Now, there are different things like Markov brains, which are like, there's a thing in the literature where people have used Markov models to model agent nervous systems. So this is like what we were taking the neural network, and we can build an agent's brain out of a neural network, and we can model sort of the behavior of an agent from sensation, which comes in the top, to some sort of effector state, which comes out the bottom. So that means, like in a agent, usually if there's information coming in, sensory information, that comes in the top of the neural network, and then your behavior comes out the bottom. It could be movement, it could be some affective state. And then the inside of that neural network operates in a connectionist manner. And this is what people think the brain operates in the way the brain operates. This is the analogy that this is why, everyone thinks there's such great promise in neural nets for modeling intelligence, because the brain works basically like this, although it doesn't necessarily work like this. A Markov model is different. It gives us this summary information of state and of probabilities of moving from state to state. It's a different model, but it's actually quite similar to a neural net in that it gives us these probabilities, it gives us these quantitative measures of state, and we can actually classify some of these weight profiles. And so the third thing I wanted to talk about here are agent-based models. And so agent-based models are models where you have what we call an agent, or an autonomous agent. And so an autonomous agent is simply some sort of computational agent. It might have a neural network in it, it might have a Markov model in it, it might have just an association between sensor and effector. Or it might just be like a little dot that has a state. Like in a lot of, in the lab here, we use something called NetLogo, which is a method for looking at, these little agents that are like, they exist on a grid. They're little pixels, and those pixels are each given a behavior or a set of behaviors. And they execute those behaviors maybe according to a Markov model, maybe according to some other type of model, and it basically tells them what to do given certain conditions. So if you have a grid where you have resources distributed randomly across the grid, and then you populate the grid with these little pixel creatures, they will interact with their local environment, and then you give them rules and they behave according to the rules. And since that environment is heterogeneous, then you're going to get some interesting behaviors that look like pattern formation. But it's all based on rules. It's not based on anything in a brain that they have. I mean, they have a set of rules on board, but it's all really kind of deterministic. But a lot of the patterns they form aren't deterministic, and that's something we can talk about later. But we also use these models called Brainberg vehicles. And these are like toy models of, I guess, animals. But there was a cognitive scientist, Valentino Brainberg, who about 35 years ago proposed that we can build these little vehicles that look like little carts or cars. And they have wheels and they have little sensors on the front. And they can model like animal behavior, basically, very simple animal behavior. And one of the reasons I bring this up is because Brainberg actually talks about modeling emotion with these little simple models. And so Brainberg vehicle can be fairly complex, but in the simplest form, you have a set of sensors on the front, a set of wheels or effectors at the back, and then just basically some associations between sensor and effector. So let's make those associations here. And that's your vehicle. It's just connecting the sensor and effector in a single connection. And it could be that they're full, you know, the right sensor is connected to the left and right tire. The left sensor is connected to the right and left tire as well. So you have this connection sensor to effector. Now, the vehicles exist in this environment where you have stimuli. And one famous example is you can have a light source, or like the sun, for example. And the sun is, you know, generating a light source in a certain direction, or it's generating in all directions. But your agents exist in this world, and from their perspective, it appears that the sun is in a certain direction. So they pick up this sensation of light. And they exhibit these behaviors they call phototaxis, which is this very simple behavior. If you see a light source, move towards it. Or move away from it. It depends on the rule. So that's all that's the only information that agent has. And it has a very simple nervous system. So the idea is I want to move towards the light or away from the light. And I have my nervous system, and it's telling me that to move towards the light, I need to move my left wheel a certain amount, my right wheel a certain amount, and the right and left sensor telling the agent the sort of the orientation of the stimulus. So that sounds like something that a bacteria would do. But of course it's intelligent in the sense that it's able to recognize that pattern or recognize that stimulus. And so it's actually doing what a neural net does, or sometimes what a Markov model does. And it's moving towards or away from this thing. Now, what happens is that over time, these behaviors, especially if you have a bunch of vehicles in the same environment, they become quite complex. And you can say interesting emergence patterns that look like emergence, or it looks like they perform collective behaviors, collective intelligent behaviors with respect to the stimulus. So, you know, they'll be moving towards the stimulus or away from the stimulus, depending on how many vehicles you have of each type, and they form these sort of higher order structures of movement, and it's really interesting. But there's this issue with behavior, and so Bradenberg actually proposed that these vehicles exhibit different emotions, so like love, aggression, hate, and it was based on these taxis. So this is kind of a rudimentary sort of definition of an emotion. I mean, you know that like human love is very complex, but in Bradenberg vehicle love, it's just basically, are you moving towards your stimulus really fast? Or, you know, shyness is, are you staying away from the stimulus, but you're not totally repulsed by it? So there are different ways, and Bradenberg proposed that if you configure this internal set of connections in the vehicle from sensor to effector, in certain ways you can have certain emotional behaviors. So you can have like this continuum from love to hate, but you can also have these intermediate behaviors like shyness or aggression or sort of warm and fuzzy, or, you know, there are all these intermediate states. So that brings us back for a minute to our Markov model, which is where you have A and B, and you have the transitions between A and B. And one thing you're missing here, though, is that A and B are maybe not the only states that exist in the world. You're modeling your states based on the world that you're observing, right? So you're observing love and hate as two states and the transition between them, or happy and sad. Now, say there's a third state out there. Say there's melancholy. And we didn't really characterize it because it wasn't really that interesting to begin with, or we didn't know it existed. But now we have to nevertheless incorporate it into our model. Let me see if I can get this right. Okay, so now we have to remap this model to have three states. And those three states then are connected reciprocally so that you have a new set of probabilities. You have, instead of having 4 probabilities, you have more. You have, I think, 9 or something like that. And so all those probabilities are A to B, B to C, C to A to A, C to C, B to B. And so it's like, you know, they're in their reciprocal connections as well. So those all have a probability. And so your probability matrix will grow. But, you know, how do you find these intermediate states? And so there's a type of model called a hidden Markov model. You may have heard of it. It's actually quite useful for, there's like sort of the plain vanilla hidden Markov model, and their variations of it. And they use a lot of intermediate sort of prediction to get to this. So they use this a lot in bioinformatics. They use this in, they use it a little bit in AI, but the hidden Markov model basically allows you to find the states in between your initial states. So if you have in a data set, you have A and B, and you know that those two states exist, could you find an intermediate state C that doesn't really exist in your original mapping, but then is in the data? You can find it from the data because the system's behaving a certain way that sort of suggests that it exists. It's sort of like when they would try to find planets early on in the solar system, and they would look at the orbits of different planets, and they'd say, these orbits are behaving so that there's an intermediate planet in there. We can't see it, but we see the effects. And so that's kind of what a hidden Markov model is. It's this seeing the effects of like a third variable in there. And so you can build these models where you find this third variable. When you find the third variable, then you can refine your model, and it becomes more, a better predictive model. And you can get these state transitions, and you can refine them, and they become more predictive, because the state transitions in your original two-state Markov model are really based on transitioning from one state to another, and they don't have that third variable in there. And so it, over time, it'll help you refine that model of prediction. So those are the two models. There are other three models that you would see in AI. There are other types of models as well. We won't get into those yet. We will talk about those later. But I wanted to go over those. And I don't know what happened to my screen share. This is what happens sometimes in these technological marvels that they get. But I'll record it, and I'll put it on, and I'll also put these slides up in the Slack, because I just drew like 3 slides of images, and some of them are kind of messy, but I think it gets the point across.
Yeah, I wasn't quite sure what to say, because I think for people who don't know anything, it would be very hard to follow without that, but thank you for staying with us during that.
Yeah.
But no, I mean, it's all very good stuff to talk about. And no, I just, yeah. Hopefully the slides will be recorded, so we can see them later.
Yeah. So we had some questions or actually some things in the chat. I guess Jesse shared. So we have empathy. This is an interesting paper that relates it to embodiment. So there's a nice paper.
It's something that came out a few weeks ago. It's not really related to what we were talking about. It's just I was going through my tabs to find something else, and I saw this paper. So for those that were interested in empathy, that's very much not. That's like a kind of in-depth paper looking at a very specific thing. Basically, in like psychology, it's kind of a hardcore psychology type of paper. So don't feel like you have to read it. Don't feel like it's just a very specific thing. It's not like a it's just something I wanted to point out there. And then I said, I reiterated my point, like, if you can't follow this right now, or you're like, what is going on, don't worry about it. It's not it's very difficult to follow without the slides. So
yeah. So Jesse put in something here about Bratenberg vehicles. So this is something that we have done in the lab, and it's so there are these models of like organisms that are sort of thought of as vehicles. So they look like little carts with wheels, and the idea was that if you look at a simple, well, I don't know about simple organism, but if you look at like, I think Bratenberg was thinking of like rodents or maybe like insects, and he was looking at them and said, what if they were vehicles? And in vehicles, we design things from the top down. We put in features, and we put in like headlights and wheels. What if those headlights were sensors and like eyes, and the wheels were effectors like legs. And what if we designed an organism that had these features, and then in the middle we had some form of connection between the sensor and effector without, it isn't a central nervous system per se, it's just a set of very simple connections. What happens and what kind of behaviors does it generate? It's a very simple toy, what they call a toy model, which is not, where we know that it's wrong, it's not correct, but it does give you some insight. And so this is what this book, is what.
Here, can you see this?
Yeah.
Can you see my screen?
Yeah, I can see your screen.
This is basically.
So this is the book, yeah, and kind of it's pretty long, and it goes through a lot of examples, some experiments. He has different designs for vehicles. So these vehicles are, they have these different. This is a simple vehicle here, but they're more complex ones. They have different types of response profiles.
I was trying to find the intro, because the intro, like the front matter, basically explains, the front matter basically goes through. I don't think this is going to be what I want either. It basically says how each vehicle is kind of about certain anatomical transitions in biology, and how they're building progressively in complexity about how things are wired differently. But I can't show it very easily right now. So
yeah, well, we can do. Actually, I was going to give another lecture. I don't know if my screen will share, but if it can, I was going to talk a little bit about Markdown. So why don't we? Yeah, why don't we? I can go into.
You can try again.
Yeah, Bratenberg vehicles a bit, but this is the information here in the chat. Let me see. And hello, Aaron. How are you? Looks like Aaron joined us. All right, so let's try sharing our screen. Can you see my screen now?
It's still freezing. I just see a blown up picture of your face, and then it's back to the blank screen with just your BA initials. So there seems to be some issue with.
Yeah, I don't know why. Well, I was going to give another talk.
Can you try to share the window as opposed to the whole tab?
What was that, Aaron?
No, it was with Krishna.
Oh, Krishna. Okay.
Okay.
Yeah, I was saying the same thing. Can you share your whole desktop instead of a window?
Yeah, I did that.
I find sometimes the whole entire screen doesn't work, but sometimes sharing the individual window of Chrome does.
Yeah, I did that. Is it showing?
Oh, no.
No. Well, I can do this next time. Why don't we go? Yeah, why don't we go to Aaron? How are you? Aaron's doing well. Why don't we get into Jesse's? Jesse had some things he wanted to talk about today. So why don't we?
Yeah, there are a few things today, and I know it's already 90 minutes into it. So thanks for staying with us, and feel free to take a stretch break and move around or whatever. I'm trying to remember to do that, and in academia we don't do that enough, as my colleagues recently advocated for. So what I will cover, I think I'm only going to cover. I'm going to do a little bit of talk about the meta. About the meta AI stuff, because that was an interesting talk that covered a lot of things today, or we talked about in the lab in general, and a little bit about New York Celebration of Women in Computing, just to kind of mention that again. Maybe frontier maps also, but there's not a lot I can say about that right now, especially in a short amount of time. So I'll talk a little bit about. Let me pull up my stuff for the AI talk. Will I be able to do this? I may not be able to share my notes specifically. I probably won't be able to share my notes because you can't see them right now. Yeah.
Well, Are you sharing now, or?
Yeah, I can share. I can share the windows. Like the window works.
Yeah. Okay.
But
All right.
that,
Yeah. There we go.
not what else. So I guess I'll just go through.
All right.
This is kind of this page sort of shows like this is like it was a preview for it. Was in the worst spot. So this happened 3 days ago, and in the middle. Just for those who don't know what we're talking about at all, Wednesday there was like a 2-hour, and you can go on Facebook and find it. It's really available. There was like a 2-hour discussion about what Facebook, aka Meta, is now Meta, and Meta's AI team is up to, and where was here we go. Yeah, this is what it was called: building for the metaverse with AI. And this is what the title was called on Wednesday. Was this specifically, and basically was a very big overview of realizing the potential of AI today and creating experiences tomorrow. It was basically, honestly, what it really was is that, hey, it's basically Facebook saying, hey, we're doing really cool stuff. Come join our team. Like, it was very much a promo. They're cutting a promo for how cool they are and what they're working on and some really cool projects ahead, and very like, you know, come work with us kind of thing. Like, it was targeted against, it targeted a lot. It was a very general public presentation for like, look at us, but there's a lot of implication like, hey, you know, the talent wars are real, and come, if you work with us, you'll be doing really cool stuff. So work with us. You know, open source and all this other stuff, and they broke it down into kind of these topics about self-supervised learning, which is the main thing that Yann LeCun is kind of trying to do, and what they're trying to get, one of their major pushes. They mentioned a lot their Universal Translator project and how that relates to diversity and inclusion and making things more accessible across language. But basically they have like some machine learning hard like breakthroughs and stuff like that. A very specific implementation that's going to be usable in terms of like very Star Trek, like Universal Translator kind of a device is basically they talked about that extensively. They talked about personal assistants that are much more human-like and can sort of have a lot more context when you're talking about things, or if you switch context, how you could, they're working on personal assistants that are much more robust and being able to maintain. If you're talking about, you know, if you're mentioning, oh, I want to make dinner reservations, could you help me find a place? And you say, well, I want to do Italian. Actually, maybe I don't want to do that. Maybe I want to shift it to next Wednesday. If you just shift context rapidly like that, the like conventional AI assistants right now will just be kind of like, oh, well, what, can you rephrase that? What restaurant did you want me to look up again? Whereas the speakers moved on to changing their plans and thinking about something to do on the weekend, as opposed to still talking about, you know, weeknight dinner plans. And so kind of just, they're working on making AI assistants and that kind of, these are kind of both sort of natural language processing type issues, and what they were doing in specific areas about person-to-person communication, and how they're working to have a system that can have a more robust translation between many different languages, many to many kind of a situation. And this is a very practical implementation of like, when you're talking about Alexa or Siri or, you know, Google Assistant, basically how to make that better through being much more human friendly in our speech patterns. And then they made their kind of obligatory open science and responsible innovation piece about their ethics, which I don't really know what to make of that. Like, it's cool that they're mentioning it, but it's very much like, hey, we're woke, we're cool, we're doing the right stuff. And I mean, I don't have any critiques of it. I'd be, you know, if somebody wants to look more in depth in that, they can. But it was all right. I listened to most of everything. The most interesting part for me was kind of this part. And this article talks a little bit more about that. Like, like we plan to show more details on Jan LeCun's vision in an upcoming paper, but basically some highlights from this are Jan LeCun proposes that the ability to learn world models, internal models of how the world works, may be the key. And for those of you looking at like Sabina and Josh Tenenbaum's work, Joshua Tenenbaum and a lot of the cognitive science people are really big on world modeling or generative models, or also like how does quote unquote common sense relate to world models, and these sort of, what are these structures or quote unquote innates maybe that have to be in place so we can have these models that are world models, and how do they get updated, how do they develop, and this also ties way back into critical periods, because you know like there are major things in human development of like object permanence. A very young person does not have object permanence in their world model. So if you hide the ball behind a blanket, or you know, hide your hands behind your face, you've disappeared entirely. They have no model for what happened. You have completely vanished from existence. And then, you know, if you come out from behind your hands, oh my God, there you are. But maybe a few months or years later, that's not a trick so much anymore, right? And just right now, like an interesting way to think about this now is like, even in current machine learning, there's a big thing like, if you just slightly shift all the pixels in an image, a lot of machine learning or image classification or computer vision models will completely freak out and break. They're like, uh-oh, all of our models for all of our training has been about images that look exactly like this and have a exactly particular ratio of pixels. You know, machine learning right now doesn't look at images the way we do. It just looks at pixels that are adjacent to each other and how they're configured, kind of. But that's a super simplification. But basically, it's sort of like if you do a very slight change to the image, and I'll segue also into how, in one of the talks I was in a couple weeks ago, someone's really interested in developing really interesting adversarial models that can help with these sort of adversarial changes, and even in terms of like printing out the picture. If you were to like print out a picture of a banana and put it on top of a sweater, would it be able to recognize the sweater as a sweater or the banana as a banana? And like things like that, and how like if you simply insert an image over another image, how can the models detect what's going on? Or does it say a lot of times current models will say, oh, that's not a banana, that's not a sweater, that's a helicopter. They'll say something totally different because it's not looking at the actual model. It's not looking at the image as a whole. And so there's a whole lot of differences in terms of what is being done in that space. So to come all the way back and go back to what we're talking about here in this presentation, LeCun spoke about world models. LeCun spoke about common sense. And this is something that's bigger now, but so there's also some really nice keywords, and I want to integrate them into something I'm doing with Cognition Futures too, but proposal for a modular configurable architecture for autonomous intelligence. These words kind of mean that, well, I won't try to define them right now, but we'll come back to them, I suppose. You know, key challenges in the AI research community in building such a system. Open science, yeah. How the world works. This is super related to a lot of things that Josh Tenenbaum and Gary Marcus are getting at, and it's kind of interesting to see Jan LeCun come a bit more around to speaking this way, because he's kind of been a critic of some of the we don't need some cognitive structures, but this is as a side note for when I talk to people about debates in a field. I think it's really important to notice that deep learning and neural networks we're kind of seen as the ultimate salvation of everything in computing. And this is this way of phrasing things is, as far as I'm concerned, a noticeable shift away from that peak period of thinking deep learning will save us. That was actually the joke. I don't know if I finished my story, but in 2017, when I went to that conference, or my first conference a long time ago, the joke, it was this big joke. It's like, oh, deep learning will save us. You don't know what to do. Well, deep learning, getting more neural network will save us. And it's kind of maybe become a little bit past that. Maybe it's a little bit outdated now. At least that idea. So there's a bit of a shift, maybe, in that sense. And this thing like common sense, like this would be a really interesting thing to compare with what Richard Sutton was saying in that paper about the bitter lesson, and kind of comparing and contrasting what are things that we have to program in, or like some innate, versus what not, what can and should we not try to do in that sense. Talk about common sense, and this was kind of an interesting structure that he has. Like, I don't really remember seeing this diagram in the talk, honestly, or maybe I just simply missed it. But this is kind of interesting collection of things that he's doing. This is sort of a, I don't know, Bradley, if you call this a meta brain of sorts, but this is sort of a there's sort of the internal stuff, and then external engagement. You get your feedback loop here, and there's like perception, which is this internal external part. I don't really know what they meant by configurator here. World model, credit, intrinsic, cost, all these different things at play. Were you going to say something?
Well, I mean, yeah, I think when you were talking this week about phenomenological models, I think this is what they're getting at here. So this is, a phenomenological model, at least as I understand it, is where you take something you don't really understand, like the brain. It's a black box, and you propose a model for it. You say, this is how the brain works. This is something that looks like something you might have put in, that might have come out of cognitive neuroscience maybe about 30 years ago. Like, you have like these boxes and parts of the brain, and you have them connected, and then, we want to find out how they work together. So, you have these big categories like perception or actor. These are things that are sort of like part of the computational models that they're using, but they're sort of assigned to a certain part of the brain. So it's a very, in that sense, it's a moving towards like a phenomenological model of the brain in terms of its function. And a caveat to that is that people have done this for, decades and decades. And, from like some of the stuff that they did with phrenology all the way to early cognitive neuroscience, to even now where you're putting in like these little boxes and saying that this is a function in the brain and it connects like this, and if we connect it like this, then we get a brain. I guess that's what they're saying here, because they have it on a human brain. So I mean, that's the question I have though, is like, is this really the way it works? And because we know that like there's some sort of general functions of different areas of the brain, but could you build something like this, put it together, and have it actually resemble anything like human cognition?
Yeah, and it's interesting because I haven't followed a lot of like LeCun's racing stuff super closely. I probably should have been more, but like that there was a definite usage of human level AI as a term specifically, and that's a very specific term because a lot of people say human like or human level or superhuman, or like there's really different classifications for the kind of AI people are striving for, and there's a lot of different camps about, well, we shouldn't even care about human level AI because we don't need it to resemble human stuff. It could just be what the best processing can do regardless of being human like or not. And there's valid points in each of these camps. So human level AI is sort of, what that really means is probably like aspiring towards adult level comprehension, I don't think it actually means like human infant level, although maybe in some cases that would definitely be a step up than what current models can do. And this really ties into, this can really set the stage for talks about like Joshua Tenenbaum's paper or some of the other paper about critical periods and things like that that other people in our lab right now are looking into. So and we look forward to hearing people comment further about that and what they're seeing when they're looking at these things. So I'm not going to really talk about that too much or really express like an expertise about it, because it's quite a lot of moving parts and all these different things. I want to quickly look at the chat because people were saying things. Okay.
People had to go, yeah. Okay. I also had a question with the world model.
Okay.
So, yeah, back to the thing that you were showing.
Here we go. This
Okay.
here.
So, yeah, so, I mean, world models, I've seen these around, and you know, so I guess what is a world model? They're looking at how the agent views the world, like how they model. I mean, I always think it's kind of vague. I think people throw it around, but I don't know what it means, like, in terms of what do we have now and how does it improve upon that? Like,
yeah, I don't really know what to say about it either. I would like, I mentioned these because I kind of like to take a deeper dive into this somehow, and I don't really know what to say about it yet. But yeah,
well, it looks like what they're doing is they're taking a model of sort of things that they, you know, like instead of training it on data, they're saying here's some things that are in the world, and then is it the joint distribution of those things in maybe the observations, or you could, yeah, so you're actually observing the world, and then you get these joint distributions that are like the area. And I'm not going to try to share my board again to show you what a joint distribution is, but it's like things that are in the world are distributed in a certain way. So like, cups and, towels and things like that are distributed in a certain location, in a certain context. And then if there's a joint distribution, or if those distributions overlap, then they're related in some way. If they're not, then they're not. I mean, that makes sense to me. Yeah, so you basically build this model in advance and you say, these are the things we should expect. Then you observe them and you get that distribution and you get the overlap in distributions. You figure out how things are related to one another. One thing I've always, I think we've talked about this in previous meetings, is, there are a lot of things in interactions with the world, especially with agents, where you don't know certain things exist. Like if I'll encounter things regularly that I don't really understand or have seen before. So, if you're doing a constrained task, that's one thing. Like if you're in a kitchen and you're making lunch, you have these different things, a knife, a cup, a towel, and you can interact with them. That's just, that's really no better than just having a data set and just training your model. But if you have, you go out into nature and you look at different, bugs, you have to classify each species of bug, or, what the feeling is outside, what's your feeling right now, the sun's shining, you're sweating, what does that feel like? There are all these experiences and things that you encounter that you can't really put into the model in advance. So, that's the thing about world models, is that, it's great that you have a model of the world, but, that world is always expanding and changing. So it's hard to, that's the thing I'm having a little bit of trouble with world modeling.
Yeah, there's a whole discussion to have about dealing with uncertainty and modeling worlds and common sense. And, I'll close on this by saying, one of the most interesting and difficult of these, I guess, challenges is it's what we always talk about as being hard. The instantiating and the details, instantiating the details of the architecture and training features for the world model. It's not. None of this is clear cut. This is all tough stuff, and no one really knows. But it's yes, we think working on this problem will result in big progress. And that's what it says. This will be, this is what someone, and one of the biggest companies in the world is saying, "Hey, this is going to be where this is the frontier we have to explore," basically. So I'll leave it at that. Yeah. Okay. Let's see. Okay. I know there's not that much time left, and I know there's a lot of people to go. So, and what would you? How do you want to spend the last little bit of time here, Bradley?
Well, I mean, Brian or Sam, did you have anything you wanted to mention or bring up, or?
I mean, I was really happy to thank you, Jesse, for going over all the stuff that Meta's been putting out, because I've been kind of following it from afar, mostly thinking, God, what do these people even think that they're doing right now? So it's really great to get a bit more insight into what's actually happening. But no, I love these neurosims. Thanks.
Yeah.
It's great.
Sam, did you have anything?
Sorry, I think I was muted. Thank you for going over all the different types of models earlier. I appreciate it. I'm going to add some of those to my research and see if they can help me in any way. So I appreciate looking at that.
Yeah. It's good.
Yeah, I'm sure Bradley can get you the slides and stuff on the screen.
And you know, don't feel overwhelmed by a lot of the content. It's a pretty hard area. You know, you wrap your head around like these different areas and what people are doing with different models. It's really just a matter of, you know, spending time reading some of the literature and like kind of, you know, one good way to do this is to just kind of go through like a certain area and then do a little mini survey of the different techniques that are mentioned. So if you go through a bunch of papers, you might look at their techniques and you might write down like what those are and the details. Like I showed you, well, I tried to show you the 3 models today of, you know, like neural networks, and then there are 2 alternative models. There are more, but I didn't go into those. You know, the Markov model and then the agent-based model. And so you can do things that you can do with a neural net with those types of models. The question is it, you know, are neural nets better? Do they, you know, they have certain assumptions, these models. Do these assumptions fit the problem you're trying to solve or not? That's really the key. And then once you get past that, you can write a paper that proposes, well, we're going to use this model to answer this question. And then it's up to your peer reviewers and, you know, doing the work that determines whether that's a good strategy or not.
Okay, thank you. I'm gonna really look into those and see, because all of the research that I found was just pretty much tailored towards neural networks, which are, like you said, they have their strengths, but they also have their weaknesses and their flaws. So there should be a little bit more of an updated technique. So I'm gonna look over the video with like the picture, because I couldn't see the picture, so should be. Thank you.
Thank you, Jesse. I know in the chat, I don't know, maybe I'll put this in the chat now, we can do this. I wanted to go over this abstract, but I can't share my screen. So I was wondering if you could share your screen. I'll put this in the chat.
Yeah.
And then we can go over this.
Which one?
So this is the document.
Don't I have open already? Yeah, okay, I had that open. Cool. I was actually thinking that one. Perfect. Yeah. Here we go.
Okay.
You see this?
Yeah, I can see it. Okay. All right. So this is the switching document. We met earlier this week about this switching theory, and so Ankit and I did a paper on this where we were working with genetic algorithms. And we worked on, it's another one of those techniques that you might use for simulating intelligence, but we'll get into that maybe another time. You know, he's designed some algorithms that use this switching between different regimes, and, you know, it would affect the performance of the genetic algorithm to explore what they call the fitness landscape, or the space of different possibilities. And so, you know, there are performance improvements, and we characterize those. So it's very in the weeds. This paper is a little bit different. This is a theory of switching. So the idea is that you have this phenomenon called switching. and you'll see it. And the idea was that, and this is something I presented on, I think late last year. The idea is that in a lot of systems, it could be like a behavioral system, it could be in the brain, it could be in biological systems, it could be in algorithms. You observe these switching events. In other words, they're switches, or they're these mechanisms that move the system from one state to another. And sometimes this happens as an adaptive result of adaptation, where you have, some forcing mechanism like the environment, and it presents a challenge to the organism, and it has to maybe have a couple of states that it exists in to survive. It switches between those states. And so in that sense, it's an adaptive feature. There are other things. You can even go to things like phase transitions in matter, where you have matter that switches from one state to another, given its temperature regime. And, so that's where we start. And then we move into things like behavioral switching. So you might switch from a quiescent state to an active state under certain environmental conditions. There is, in the brain, you have switches where you have, you're paying attention to one thing and you switch to another thing, where you can switch back and forth. And there's strategies that the brain takes to be able to make that switch. And those are often actually couched in terms of like trade-offs or optimization. And so the idea here is to develop sort of a theory of switching. And this is, this is a challenge. I know Brian's really interested in this. And the challenge is to write a theoretical paper. And so what we're doing here is we're writing a theoretical paper that has, like a statement about what the theory is, perhaps a summary of the theory. So it could be a theorem, or it could be a verbal description. So you can use mathematics, you can use a verbal description. You could even use like a model to summarize it, like an agent-based model. People have done that. But the idea is you have this core idea of what the theory is, and it should be stated clearly. And then you want to grab examples from the world. And so, I mentioned this yesterday as a matter of like having a theory of snowfall, which we have, but let's suppose we didn't have a theory of snowfall. We would go out and we would say, I think snowfall, I think snow occurs because of this reason. And it might be correct and it might be incorrect. But the way you evaluate that is then you observe the world. And you take observations of the world, different contexts, different places. You may even have to observe different planets to make sure that your theory is correct. So you have all these examples. And the idea is you want to fit these examples into your theory. Your theory should be broad enough so that it fits your examples in. It shouldn't be very small. Like, I can explain one, snow in one context, but I can't explain it anywhere else. So if you have a theory that depends on you being in the polar regions of the Earth, that's not really a good theory because it doesn't generalize very well. It's kind of like what we see in machine learning with generalization. If you can't generalize well to something, then it's not a very powerful theory. And thus it is with these AI models. If the AI model can't generalize, to different tasks or to different contexts, then it's not really good. Actually, AI is really a theory of intelligence. It's not necessarily intelligence, it's a theory of intelligence. It's like, how would you, if you had like an intelligent mechanism, what would it do? I mean, that's my take. Maybe that's controversial. But back to the paper. The paper then is going to be like, we're going to go through the theory, describe it, then we're going to get a couple of examples. And then what we discussed is like targeting a close deadline of a couple weeks from now, or actually this week, for a 2-page summary of this. And then maybe a longer term paper where we have 4 or 5 examples we work out. So we've identified some examples, and if you're interested, there's a channel in our Slack. It's the switching channel. I can't remember what it's called. It's switching paper, I think.
I think it's called switching paper or something.
Yeah. And so we were discussing the examples in there. So if you're interested in being involved in this, really what we're looking for is working out the examples. So if we can work out some examples, we need to go to the literature and like identify like what is going on in these systems, why do we think they're switching, and then, you know, some literature review, maybe some analysis of it, and then, you know, we'll have those examples, we'll have the theory, and then also at some point we'd like to model this. But I think that's down the road. I think the theory building, and I wish I had better theory building materials right now, but I don't. We don't have those. So I'm going to kind of go through this ad hoc like we've been doing, and we'll eventually get those materials in place. But so we're working on this, and there's a deadline. We're trying to hit a deadline of like Monday. I don't think we're going to make that, but we can try for a very short paper. And then a longer term goal is to get like a longer paper with multiple examples and maybe some modeling, but we don't really know yet. It'll take shape. But if you want to be involved, that's where we are with this. What else did I want to say about this? Yeah, so I think that's it. Thanks for sharing the screen, Jesse. That was good. Yeah, so that's coming up. And we have our A-Life conference deadline, which is coming up, I guess, Monday. They may extend it. That's where we want to target this 2-page switching paper. And there's another paper that I put in the Slack channel, I think for MetaBrains. I think this is something I tagged Jesse in, because he's a co-author on this. But it's another MetaBrains paper that I was working on. And, you know, I put you on as a co-author because you were working on this together. So if you could take a look at that and give feedback, the deadline's coming up, but that's something we'll work on longer term as well. I don't know if we'll get accepted to A-Life with that paper, but it's a little bit of a strange, that's the one I showed last week, where it had the folding and the layering and all that. And I think it's kind of an interesting approach, but I don't know if they're going to go for it, because it's kind of, I don't want to say out there, but it's not, maybe not typically what they have in the conference. And, you know, if you're in a situation like that, a lot of times it's about, like, you have to really show a lot of, like, work to get there. Like, you have to have, like, a lot of simulations to get there. So I don't know. We'll see.
Do you mean in order to prove the layering, folding, and information correspondences that you're talking about in the paper?
Well, I think it's more along the lines of, like, breaking through to people. Like, I think I mentioned yesterday that, like, people will see, when you do theoretical papers too, you know, you'll get, like, examples from different fields, and people will, if they're from a field, they'll see that example and think, oh, that's what it is. And then they'll see another example and they'll say, well, wait a minute, that's not what it is. So it confuses people, but it does so because they're in the mindset of, like, this is my field and this is how I think about it. And then how do I think about it in another way? And that's a tricky thing to get to. Like, that's a tricky thing to sort of communicate. And it is, you know, some of it's communication, but some of it is just kind of like having a really earth-shattering result. So that's kind of the challenge there. Yeah.
And is that connected to the theory building materials that we're trying to kind of gather for the switching paper, for example?
Well, no, the theory materials are something that we'd like, and Jesse and I talked about this yesterday, that we want to have, like, maybe a separate education group. You know, like we have in the lab, we kind of, one of our hallmarks is that we have this emphasis on education and mentorship. And we don't really have a project on it or a group, but we're trying to go in that direction so that it's like a separate own thing, but it's not really like a research group that we usually have. But under that banner, we'd like to put, like, formal materials so that in the future, maybe people can see that, you know, here's how you build a theory. There are materials out there, there are books and things, but it's very sparse. I was surprised at how it's just really not accessible in the way we we'd like. What we'd like to do is have like a way for people to engage these theory building techniques. Like, you know, if I want to build a theory of something, how do I do it? And then how do we get from beginning to end? Yeah, that's the talk, that the theory building for data science talk. And that grew out of the idea that data science is very empirical, almost to a fault. It's like, you think about data, you think about how to analyze it, the process. You don't think about like why you're doing it, or the assumptions that go into it, or that your data that you have, whether it be like, grocery store usership data, or, facial recognition. I mean, there's a history of using algorithms and techniques on a broad spectrum of problems. So like I could use one algorithm on anything. But the problem with that, of course, is that every bit of data usually has like some theory behind it. Like, there's a theory, for example, of, there are different theories in different areas, in different domains. And so when you apply an algorithm very broadly like that, you're ignoring that sort of history of the data, or the sort of the larger picture. And so what I was advocating for there was to theory build on your data set, and just kind of figure out what the theory is behind it, and maybe that's taking from the original field, or, more likely, building kind of an ad hoc theory on top of your analysis. And so that was something I presented on several years ago, and it was, and again, if we have like a way to kind of communicate this to a larger audience, get people, so that they know that this exists, that they're aware of it. That's, I think, what we want to do there too. Yeah. Okay.
Well, I just brought it up because I love that presentation.
Yeah.
Been using it as kind of like a guideline for how to move forward, mostly with AI research, because so much of it is database. It's great.
Yeah, I actually haven't really, I haven't really thought about it in a while, and I now that you mention it, I feel like I want to do something more with it, because I think it is useful, but I don't know exactly where it's breaking through. Then that's always a challenge, but...
Yeah, I was just going to say it might be like a nice starting point for developing ORL educational materials, because it is coming from this perspective very specifically. Anyway, it's great.
Well, thanks. Yeah. Okay, well, let's wrap it up for today. Jesse or Samantha, do you have anything else to add, or?
I don't know if Sarah's saying anything. No, not really. Next week, I think I'm going to have to do a little bit more on... I'm going to need to talk about New York celebration computing a bit more, like earlier, just to do that.
Yeah.
But that's all right. There's a lot of things in Frontier Maps that are... There's a lot of things that... It was a big week in terms of moving some things forward in the lab and in some of my projects, but I'll say more about them, like either in Slack or just next week too. So
yeah. Okay. Well, thanks for attending, and I'll put the recording up because I know that we had some trouble with the technology. That's normal. That's just the way it is.
yeah.
So, okay. Well, thank you for attending.